Should I keep my glasses? Okay.
The best feeling. Oh, when I get to like incoming machine learning into your
I mean, I would hope. No, it's okay. We're humans. We're humans.
I think it's because everyone was I don't know where they did.
Very quiet. Very well behaved class when it comes to quietness.
Sarcasm.
Okay. There's more here than I was expecting, considering all the emails about COVID cases that I can get. Hopefully, we're able to make it through the exams. And there are rumors around that the department is coming up with a. Normally, if you miss the exam for a medical reason or something like that, there's usually one or two students and we have alternate exam and somebody, you do it another time. But they may be coming up with some more formal plan, considering how many people are missing. 10 emails from the 3 group class students on Monday. 10. I assume that most of them are COVID isolation. Connection today. This thing working okay? It seems a little quiet. Overall volume. Strange getting these touch screens never work properly. How's that now? Any different? Everybody in the back okay? Yes? Yes? Yeah. Okay, right. So we had this inequality, which I haven't finished writing up yet. So here's today's agenda. We're going to finish up number 1. There's an example to do. Number 2, we're going to get some more inequalities. And then there's some remarks. I need to show you how to use this thing. So there's 2 bits to it. What does this do? This is saying that considering the inaccuracy in the coefficients of A and B, what's the net effect on the solution? And this bit, well, that's our exact system. And we're saying, well, suppose A is adjusted by some small matrix. It's not exactly what it says it is, and some perturbation of A. That's the delta A. And similarly to B, suppose B isn't fine. Right, so in the case of the two lines, remember we had the slopes, that was changing the A, and the B was the intercepts. Then there's this bit. Oh, here you'd expect that, like, initially maybe you'd think the relative change in X, or the relative difference in X here, how much does X change because of these changes in A and B, might be somehow related to the sum of these two things. Well, it is in this sense, but there's another factor in there, which is this bit in here. And the kappa is the condition number and you can see that if that is large, then this bit could overpower the rest of it. In fact, the inequality might be very large. The upper bound on the left-hand side could get very large. And generally, you want to keep kappa small. You don't want to have kappas that are in like high orders of magnitude. There's one condition on this. The easiest way to remember it is that you want this thing to stay less than this, otherwise it becomes negative and it doesn't work. And the condition is that kappa, how did we actually write it? We wrote it as 1 over kappa is greater or equal to delta A over A. So this, in other words. And that puts a bound on how much you can modify A, or how inaccurate the condition, the coefficients in A can be, considering the condition number. So for instance, if this is 10 to the 5, then this is 10 to the minus 5, so the relative change in A before this condition is no longer valid is quite small. So you need to know the coefficients pretty accurately. If kappa is 6, so about 10, say, then this will be 0.1, and you can have more freedom, depending on how big this is. This is the relative change in A. This is the relative change in B. And this is a condition that this guarantees that A with the perturbation is invertible, remains invertible. And you can see what I was just saying was that with this condition, that says that this thing doesn't hit 0. It should really say less than here, I think. But still, you don't want that to be equal to 0, and you don't want it to go negative, otherwise what we did was the inequality fails. So this is to be avoided. Now how do you use this on a problem computation? Well, there's two ways. One is in practice. In practice, you have some knowledge about how accurate these things are, and you know what your system is, and you know the condition number of A, that can be calculated easily, and therefore you can put an upper bound on the relative sensitivity of X to your problem. So that's a practical use. And for that, you don't need to know what the left-hand side is. This you can calculate without knowing that, and it puts a bound on it. It's like a worst-case scenario, if you like. The second way that you're going to use this is for an exam-type problem where you're given a little system, a 2x2 usually, and you're asked to demonstrate the inequality, and you're given the delta A and the delta B, and at some point in that, you'll be asked to say, well, what is this? The inequality predicts the worst case. What is this actually in real, like, something you don't know that when you're using this normally, but in this case, in a simple system on the exam, you would also be asked to calculate what that is. So to do that, you have to calculate the solution of the system. You'll be told all these details in the problem. Now you can say that all systems like that should be solved by inverting the coefficient. We have to follow the instructions. But that step of finding the left-hand side is simply to illustrate the inequality. See how good it is. There's still a problem. This is the exam type problem. There's one in the textbook, which is good enough, but it has details missing, and I like to go through it. Fill in some of the blanks. There's a matrix. B in this problem, you're told what the exact solution is, meaning the paper solution, not numerical. 1, 1. Well, you can see that that's correct. On the exam, you might be asked to find that by inverting A. So there's two parts to the problem. The first is apply a perturbation to B, so you don't touch A. Delta B is 0.01. So this B becomes this plus this. And you're asked to find the exact solution of the perturbed system and illustrate this inequality, something along those lines, with details provided. I always give lots of detail. So just follow the instructions. It's an exam problem. But first of all, to find the exact solution. Of what? A plus, there's no delta A. AX equals B plus delta B. That's the first step. And I said in the notes here, use exact Gaussian elimination or invert the coefficient matrix. We'll be told which to do on the test. And we've used a different name for this because it's not the same X. I'm calling it X hat. It's a different system. And this solution, X hat, is quite different. One example of these lines are very close. And we've moved one intercept a little bit and the solution has changed quite drastically. So what is the delta X? And delta X, it doesn't matter which way you do it, but here I've done X hat minus X. Sometimes it's X minus X hat. All that matters is the difference, the magnitude. So this is this minus this, which is 3.99, 1.99. That's X, delta X. So we can now calculate the delta X over X on the left-hand side. That. Stop me if anything is not clear. And this is all going to be guided by the instructions in the problem. It's told you to do this first. It's not just doing things at random. You need this over this. And we can now calculate it. This is delta X. What's its norm? You'll be told always in the problem which norm to use, so everybody does the same one. It'll be always the row sum norm in norm. So it's 3.99. And the norm of x here, this is our x, 1. So this is 3.99. The left-hand side of the inequality, which we don't need to use the inequality, we've now got it so we can see how good the inequality is. Yeah.
Is delta x always x hat minus x?
Well, I had to look to see what I'd done here, because some books do it the other way around.
Some do x minus
All
x.
that matters is what's the difference between these. And here, when you get the norm, it's going to be the same whether you do that plus or minus.
Okay.
So it doesn't really matter. Okay, what's next? Inequality, things we need. We need the kappa, and that's calculated from A. Brush. Here. I'm going to leave this up. And that. To get the kappa on a test, you would have to invert A, and typically, you would be given this, you'd be asked for it. So you would begin by saying, invert the coefficient matrix to get the exact solution. And you'd have the inverse here, and you'd find its norm, put it here, norm of A here, then you get the condition number. And when you do that, you get 1197 for the condition number. Okay. What else do we need? In this inequality, do we have any change in A in this part of the problem? No. It's only B that's changed. So that's 0, that's 0. I need delta B, and I need B. I can do the right-hand side. Delta B .01. Oh, and norm of B is 1. That's everything we need. Delta N is 0 in this part. I'm leaving out some of these things so we've got them handy. Going from here, we apply the inequality. Left-hand side is here. .99 is less than or equal to kappa. There's a 0 there. And this. That's just 0 point. All right, so something doesn't quite right here. Yeah, this. How come nobody spotted this?
Too easy writing.
That. And remember I said it had to be consistent with this? Wasn't before. It was error. Good question?
Yes, I was just wondering how we knew that delta A equals 0.
Because in this part of the problem it says only B is perturbed.
Only B is...
Perturbed.
Oh, okay.
Okay? There's no delta A. So here this is 1 minus 0. That's better. So that's 11.97. It's correct. And this isn't a bad upper bound on this. So this is the worst case. Now we do the tricky one. I don't know if we can keep all this stuff up. We won't need that again. Why don't I need this again? We have a different system. In this part, we're asked to perturb delta A as well. Give a delta A. So, and the one you're given is one of the problems with exams. I like to point out common errors. The common error is to not understand the wording of this problem when it says, in addition to the perturbation of B, apply a perturbation to A. And for some reason that doesn't always sink in. There's confusion by more than one person will slip up on that and not understand what it means. All it means is that you start with the B, that was the easy one, there's no delta A, and then you also include the delta A. That's the sort of approach. But we've got a delta A. We should check this inequality. Do that first. This. Check. Again, in the test problem, it'll say, confirm that A plus delta A remains invertible using a result, state the result, and then check it, something like that. So you need to check, because otherwise the problem is not possible to do. That result. Norm of this is this plus this absolute value is 0.002. Same here. And norm of A is 3. Kappa is 1197, this is 1500, so we're good. Condition is A plus delta A remains invertible. Okay. Next, you asked to illustrate the inequality in this problem. It means we need the left-hand side. Delta x will be different because we've perturbed both A and B now, so it's a different system. We're looking at A plus delta A times x hat equals B plus delta B. We need a different one. So we have a third matrix that we have to invert 2 by 2. Exact solution of, and again, it's the perturbed system. In this case, meaning A plus delta A. I'm going to call it x hat again. It's not the same x hat as in the previous part. Equals B plus delta B. To get the exact solution, if we follow the instructions and invert the coefficient matrix, which is this one. Plus that, plus that. We have to invert it. And again, cofactor method is pretty simple for that. I like to use that one. I'm going to have to rub this off. the x hat you get inverting a plus delta a, multiplying by b plus delta b. Again, very small changes, very significant change in x. We can calculate delta x now, the new delta x. X hat minus x is this. This minus 1, 1. That. And what else do we need now for the inequality? That's right, the inequality. That's the left-hand side. And we know this now, but let's assume we don't know it for the moment. Question?
Sorry, could you repeat how you determined x hat?
I calculated that inverse using the cofactor method. That's the easiest way with a 2 by 2. And I multiplied by b plus delta b. And that's our x hat.
Okay, and you said that this is a different x hat from part A?
It is, because we've changed both a and b now. In part A, we only changed b, so we have 3 different systems. We have the original exact system, we have the one in part A, which was changing just b, and we have now changed both A and B matrix. So we have 3 different systems. I've called it the same name. The name is the same. But let's assume we don't know this for the moment. We do know it because it's right here, 11.91 divided by 1. So let's continue.
Why is it x hat and not just x? Like, is there, like, since it's delta, like, will you always give us x hat, or will there ever be a time where you give us, like, x?
I'm going to give you neither.
Oh.
If you're given A and B,
Okay.
you can calculate x by inverting A. That's the first thing. Okay?
And,
And then in this new perturbed system, here it is. You need to take A plus delta A, and you're given delta A, so you take this, and you get a new matrix. You find its inverse and multiply by B plus delta B. That'll tell you what x hat is.
oh, okay. So x hat isn't the same as x?
No.
No.
X hat is the solution to the perturbed system.
So it's not like a unit vector?
No, no, no.
Oh, okay. Okay.
Just the name I called to the solution of the perturbed system.
All right.
And the difference between x hat and x is the change in x, because of the changes in A and B.
All right,
And
thank you.
or B. So we need the condition number. One minus the condition number times the relative change in A. Relative change in A, here it is, this number, 1 over 1500. Let's put the numbers, the actual numbers in. 0.002. And 3. So that's the sneaky bit at the front. And then we have the bit with the relative change in B and the relative change in A. So what's that? That will be 0.002 over 3. That's the relative change in A. Plus the delta B. 0.01 divided by 1. Those are all the numbers on the right-hand side. And when you calculate that, it's consistent with the notes. This number is 63.2. And you asked to illustrate the inequality by finding the exact solution so you can calculate the delta x, the relative change in x. We already did that. It's 11.91 divided by 1. So this number is less than or equal to that one. And this is the worst case scenario that we predict if we didn't happen to know this, which you don't do when you do the numerical problems. You only know this because it's a trivial problem. You can do it by hand. So you can see it's not a bad upper bound. Any questions? That point is the one which is often misunderstood, or it doesn't sink in or something, that what you've got is the two ways to use it. There's the one where you use it in practice because you've got a big problem and you've solved it numerically, and MATLAB is telling you something bad about the matrix, or maybe you're suspicious that the matrix has a big condition number and therefore could be inaccurate on the x. And so you need to use it. That'll give you an estimate. In exam problems, you have a simple problem where you can get the exact solution to illustrate that this actually works. Those are two different things.
Will we be given this formula on the exam?
No.
Oh, okay.
This formula you need to remember.
It's good to know, good to know.
It's not difficult, despite having put the title on here when I came in. Kappa, 1 minus kappa, relative change in A, relative change in A, relative change in B, relative change in X. It's not hard to remember.
Memory sucks.
Okay, next topic is number 2, accuracy. It's always touch and go whether there's enough time to derive the inequality. I think we can probably do that. I'd like to show you the derivations because they're simple and it helps you to realize that they're actually not that, they're not magic formulas, they just follow from what you've known about the problem. And the question with accuracy suppose you've got the system x equals b, you put it into your MATLAB system and you get an answer. How do you assess the accuracy of the solution? You don't know the exact solution, you only know what the approximate one is. That's an approximate solution calculated with floating point arithmetic. You don't know the exact solution, so there's no way to compare it. It's a bit like the same problem with solving differential equations by a computer. You get an answer, but how do you say, no, if it's a good one or not, how accurate it is? One of the tricks in that is the MATLAB software will calculate the solution two ways. It'll do it one way and it'll do it a slightly different way, and then it will compare the two. And that gives some idea about whether the answer is accurate. But that isn't how it's done with linear systems. We have other inequalities which tell us about accuracy. And they're okay up to a point, but they have limitations. The important thing is to understand the limitations of the approach to assessing accuracy. So we have the same system. Everything is there, x equals b, and its exact solution x is available but not known, and A is invertible. That's the setup. X is unknown. And in this case, x hat is some solution which you've obtained by numerical methods. And it's supposed to be an approximate solution for x, which is unknown, and we need to know how accurate is it. That's the question. That's our question. How do we assess the accuracy of x hat when we don't know x? Okay. In a nutshell, let's say IE, and this is symbol E, x hat minus x. Use the symbol E because that's what they use in the book, but also it makes more sense to call it something else because we're not perturbing anything here. We're just taking two things, an approximate solution and the exact solution, and we're taking the difference, and that's the error. And this discussion says, no, we're not able to calculate error. Reason? The x is not known. We can ask a different question. Suppose we put our x hat into the system. And we have the residual. Did we ever define residual?
No.
Did we define residual? Okay, it's what you get left when you put the approximate solution into the system. So x hat is supposed to satisfy A, x hat equals B in some approximate way. And we can take the difference between those two sides, and that's the residual. Symbol R. We put this in, and if it was an exact solution, we'd have 0 then. But it's an approximate solution, so we have some number.
What is this?
That's called the residual.
Yeah, what's the residual?
And that's the approach that we'll take, and it gives us a result with some limited usefulness to it. Let's jump into it. And so what we're asking is, if this is small, does that imply something about how good x hat is? Small in some sense. Does that imply E is small? Again, in some sense. In some sense doesn't really cover it though. We need to have a quantifiable result. And so we could say, well, what about the relative values of these things? So what would we compare them to? What would we compare them to make relative values? Well, this one we could compare to B, and this one we could compare to X. And because we're dividing things, we need to put norms in. This is the relative residual. Does it imply something about the relative error?
Oh, damn. Oh, okay. Yeah, nice. Thank you.
So in other words, if this is small, does that imply somehow that this is small? And this is the one that you cannot calculate because you don't know those things. But these things we can't calculate because they depend only on the approximate solution and the coefficients of A and B. So this we can calculate and ask the question, if that's small, does that mean that this is? And the answer to all of those questions is maybe. So the best we can do is to come up with an inequality that says when maybe can be ignored. And what we produce out of this is a sandwich, where the thing in the middle is the relative error, which we don't know, and then we have a lower and an upper bound on it, so it's a sandwich. And unfortunately, sometimes there's too much meat in that sandwich. And that's when maybe happens, when maybe answer becomes no. Maybe becomes yes. We'll see. Let's develop the inequality. And this one is a little is not fiddly in the same sense as the first one, but it requires going in several different pathways and then putting them all together. But it's only using the basic ideas. So let's put it here. We'll develop it here. What we're going to do is get a few inequalities and then we'll put them all together into one big one. Starting point. Definition. I'd like you to be clear on where each step comes from, so you see it's not magic. This is the definition. And what is B? Can we replace B by something? See, what we're trying to do first is to get something that involves these two quantities. And then we'll repeat it again and we'll get something involving these two and then we'll combine them. So what about B? Is there some way we can get rid of the B? What is B? It was on that board, I rubbed it off, the original system. AX equals B was the exact original system, the exact solution. So here we've got B is AX. That's the exact system. Then we do this step, which is obvious. What do we have up there now? X hat minus X. And here it is. That's E. X hat minus X. Definition. That gives us two things. Before we proceed, we have colored chalk. I remembered it. Nope. Oh well. Must have fallen out of my pocket. That's bad luck. Colored chalk. Oh, there's some here from yesterday. We're going to go to something else first. A is invertible. So what can we say? E equals A inverse R. A invertible. These are the reasons. Okay. Now we apply the norms. We want inequalities are going to involve things, the numbers, so we apply norms. And we have our magic things, if you like. That one. And the other one with the triangle inequality type thing. Everything in this whole section comes from those two. So here we've got a product of two things. We can use norms and come up with an inequality. So this one gives that. This one And given how good you are with inequalities, after having been through 1 to 18, and had to review some school stuff, you can combine those into a single inequality. And in the middle we'll put E. So we'll move that one across the other side. Here's where we need the color. We take this and this, put them together and make one inequality with this in the middle. So this one says norm E is less than or equal to this over this. Correct? I think I said less than or equal to this. This goes to the other side. So we get an R over A with an E in the middle. So, on the other side, we have the one with the inverse. This guy less than or equal to this. That's the first step. That relates the relative residual to the error. Doesn't give us what we want though, does it? We want this. So we repeat the same sort of idea, so we get an x, and then we divide the two inequalities together. Let's do the next one. We'll start with ax equals b this time. And then we'll split that up using norms. This guy. That's step 1, if you like. Step 2. It's a little easier, we don't need all the preliminary stuff. X equals b, and we want to take the norm. Write it the other way. This equals this. And we get that. There's an inverse of this, just like there was here, because A is invertible. So we get x equals A inverse B. We take another inequality with norms. And we get that. This guy can move down here, and then we have B sandwiched in the middle. That one we want. That'll be a false start, wouldn't it? Because we don't want B in the middle. We want to get something where we have in the middle the x, norm x. So we can combine the two into a single inequality by dividing. So we need to put the x in the middle. We've already got it here. That means the x here has to be in the middle to divide by that one. That's too skimpy there. Give that room. This is the, I'll leave that up. That's the goal we're looking for in the middle. This one, divide by that. And combine. Fishy, yeah? I told you it was fiddly. I mean, lots of things are true, but it's not necessarily what you want in the end result. In the book, they gloss over all this. What have we got here? I think we've done this one backwards. It's still true, but we're not using it this way. This one we need. We divide, of course, because we want to put the 1 over x here. That's why this is wrong. This is true, but we want to make it the other way. So this one becomes the 1 over norm x. We have to change the direction so that the two things flip. Is this. Notice it flips. And we don't want this guy here. We want it the other way. That's what we want on one side or the other. And that's going to give this over this. That's correct. Yeah, for this one, we just moved this to this side and vice versa, so it doesn't change. This one, we divided the whole inequality, so we had to change the direction. So this is our left-hand side, this is our right-hand side, and this is in the middle. What I wrote here is still true, but it's not what we want. Let's combine those two. Left-hand side is there. Like this. Right-hand side, norm A over B. And in the middle, 1 over norm of x. That's the second inequality. This one relates relative residual or residual to error. This one relates the x, the exact solution, to the other terms here, the b and the b. We can combine. Like a big sandwich. Make sure there's no errors in this. Oh, we're good. And how did I know the other was not what we wanted? Well, you'll see, we'll put them together. Combine again, 2 boxes. The left-hand side is this times this. The inside bit is e over x. Right-hand side is this times this times this divided by this. Now, how did I know when I said that didn't look right, it didn't look like we were going the right way there? How did I know that? We'll come back to the question in a second. How did I know that what I had before was not what we wanted? What clue was there? What's this? You should recognize this is now combining these two. What's this guy in I circled in the box?
The K.
Yes,
Whatever K.
that's the kappa, the condition number. So the inequality can be written even more simply. Let's write it like this. There it is again, kappa. And that's the final result, which is very, very clear and easy to remember. It says that the relative error, which is unknown, is sandwiched between kappa times the relative residual and 1 over kappa times the relative residual. That's our inequality. Now, why did I write maybe over here? Can you think of a reason? If you think about that while you get your coffee, and there was a question before we start. Was there a question somewhere? I saw a hand a few minutes ago.
Oh. So you said that the top equation represented the residual error, relative residual to the error. What did you say the bottom equation represented?
Bottom here or bottom here?
The first one.
This one?
Yeah.
Well, it relates. This sandwich is in the middle to e, and this sandwich is in the middle to 1 over x, and we need something in the middle which is e over x, right? So I multiply these, and I multiply these, and I get that box. That's all.
Like a convenient way of like.
Well, you don't have to remember these. You only have to remember that one box. So everything I've done in this entire section is combined in this box, right? So that's what I suggest you learn. Think about why I wrote maybe. If I want to assess this, and I know the residual, the relative residual. What's the maybe part of that? Go and get your coffee. And we'll do an example of this. I still have midterms here if you haven't picked those up.